Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Ahmad Nauman, and today I will give you the second lecture about magnetic properties of advanced materials. And this lecture is continuation of our previous lecture, and we will start where we left off in the previous lecture. So next we have a third type of magnetic substances known as ferromagnetic substances. In the previous lecture we studied two types of ferromagnetic substances known as diamagnetic substances and paramagnetic substances, and today we will study the remaining types of magnetic substances. As in the last lecture we discussed that diamagnetic substances are repelled by the applied magnetic field or the external magnetic field, and we also learned that diamagnetic substances have no unpaired electrons, and those diamagnetic substances, they cancel out the magnetic moments of each other because they have unpaired electrons, so that's why they have zero net magnetic moment. In contrast to diamagnetic substances, we learned that in paramagnetic substances there are unpaired electrons, and they align in the direction of the applied magnetic field when we put them in the external magnetic field. However, when the external magnetic field is removed, those domains come back or return to their original state, so they lose their magnetization after the applied magnetic field is removed. So today we will now first study about ferromagnetic substances. They are different than both diamagnetic and paramagnetic substances in the fact that these, when placed in an applied magnetic field, their magnetic moments align along the direction of the applied magnetic field, and even when we remove the magnetic field, they although lose some of the magnetization, they mostly remain their magnetic moment. And हमने पढ़ा था जो लास्ट लेक्चर में जो वाइस डोमेन्स होते हैं कि जिनके अंदर जो इलेक्ट्रॉन्स होते हैं और जो उनके मैग्नेटिक मोमेंट्स होते हैं, दे आर अलाइंड इन ग्रुप्स. सो जो फेरोमैग्नेटिक सब्सटेंसेस होते हैं, इनके अंदर एक जो करेक्टरिस्टिक है जो इनको डिफ्रेंशिएट करती है बाकी मटेरियल से, वो ये होती है कि इनके जो डोमेन्स होते हैं, एक तो वो अलाइन करते हैं विद द एक्सटर्नल मैग्नेटिक फील्ड, एंड आल्सो दे इंटरेक्ट विद द नेबरिंग डोमेन्स एक्चुअली, एंड दे ट्राई टू अरेंज देमसेल्फ पैरेलल टू द नेबरिंग magnetic field or magnetic domains. So that's why when they are placed in magnetic field, they get magnetized, and after the external magnetic field is removed, they lost some of the magnetic moments, but overall they retain the magnetization, and this is the reason such kind of substances are also known as permanent magnet. So the basic requirement for a material to be magnetic is that it should have some unpaired electrons. So thus ferromagnetic substances have unpaired electrons, and the spins of all the unpaired electrons are parallel in the ferromagnetic substances, as we can see in the diagram, in which we can see magnetic moments of electrons which are parallel to each other. And examples of ferromagnetic substances include iron, cobalt, nickel, and chromium dioxide. So these are the examples of ferromagnetic substances which retain magnetization even if the external magnetic field is removed. In next slide we will go through some animation about ferromagnetic substances, in which we will see how the magnetic domains arrange themselves according to the external magnetic field, how they react to the external magnetic field, and what is the effect of external magnetic field and temperature on the magnetization of ferromagnetic substances. So let's see that now.
Ferromagnetism. In ferromagnetic materials, the atoms contain more number of unpaired electrons. For example, iron contains 4 unpaired electrons. Due to this, the net dipole moment of an individual atom is more compared to atoms in paramagnets. The dipole moment of one electron strongly interact with the dipole moment of the neighboring atoms and align themselves in a common direction. This small group of atoms with dipole moments in same direction is called a domain. A ferromagnetic material as a whole is made up of very large number of such domains. In the absence of external magnetic field, the dipole moment of different domains are oriented randomly in different directions. The dipole moment of one domain cancels the dipole moment of other domains, so that the net magnetic moment of the entire material is zero. In the presence of external magnetic field, the domain starts to align in the direction of applied field. The magnetization intensity becomes non-zero. Currently, since the external magnetic field is weak, only one domain has aligned with the external magnetic field. As field gets stronger and stronger, more and more number of domains start aligning with the external magnetic field. The magnetization intensity goes on increasing. Then, for a particular strong magnetic field, the magnetic moments of all the domains get aligned in the direction of magnetic field. Now, the material is at its ultimate stage of magnetization. Now, magnetization does not increase even if the external magnetic field is increased. This stage is also called saturation of magnetization. Just like paramagnetic materials, ferromagnetic materials are also influenced by temperature. When a ferromagnetic material is heated due to thermal energy, the dipole moments within the domain start coming out of the alignment and become random. The randomization goes on increasing. Then, at a particular temperature, the domain structure becomes completely destroyed and the ferromagnetic substance becomes paramagnetic substance. This particular point is called Curie Point. Curie Point or Curie temperature is defined as the temperature at which a ferromagnetic material becomes paramagnetic material. The Curie temperature of iron is 1043 Kelvin and for cobalt is 1394 Kelvin.
So in antiferromagnetic materials, for example, we have manganese oxide, we have cobalt oxide, nickel oxide, or copper chloride, which are given on the screen. So they show that the antiferromagnetic materials are mainly the compounds of two or more different atoms that occupy different lattice positions. So the important thing which you should be you should know that the antiferromagnetic substances actually have unpaired electrons, but the atoms which have magnetic the two atoms which have magnetic moments and that are equal in magnitude and they are in opposite direction. So what happens that they cancel out each other. So what are antiferromagnetic substances? In समरी हमारे पास जो है वो मैग्नेट ये कंपाउंड्स होते हैं डिफरेंट मटीरियल जिनके अंदर दो डिफरेंट तरह के एटम होते हैं. फॉर एग्जांपल कॉपर है, क्लोराइड है, निकल है और ऑक्सीजन है. सो व्हाट हैपन्स दैट दे हैव अनपेयर्ड इलेक्ट्रॉन्स एंड दे हैव देयर मैग्नेटिक मोमेंट्स, बट व्हाट हैपन्स इज कि जो उनकी डायरेक्शन होती है वो एक दूसरे की डिफरेंट होती है और उनका जो मैग्नेटिक मोमेंट होता है उसका मैग्नीट्यूड ऑलमोस्ट सिमिलर होता है. दैट्स वाई दे कैंसिल देयर इफेक्ट एंड रिजल्ट इन द जीरो नेट मैग्नेटिक मोमेंट. फॉर एग्जांपल you can see in this diagram कि हमारे पास जैसे आप देखें कि जो फर्स्ट डायग्राम है it has the magnetic moment in upward direction, lower next is the downward direction, same is upward, downward and that continues. So what happens is the magnetic moment of these two different atoms which are in opposite direction and have almost similar magnitude, they cancel out the magnetic moment of each other and thus we have a zero magnetic moment and it doesn't show the magnetic properties. Have another kind of ferromagnetic magnetic substances which we call as ferromagnetic substances. So they similar to the antiferromagnetic substances, these ferromagnetic materials are also made of atoms of they are compounds of different atoms which reside on the different lattice site, and they also have the anti-parallel magnetic moments. They have magnetic moments whose direction is different. But जो मेन डिफरेंस है यहाँ पे फेरी मैग्नेटिक मटीरियल का और एंटी फेरोमैग्नेटिक मटीरियल का वो ये है कि एंटी फेरोमैग्नेटिक मटीरियल्स दे हैव टू डिफरेंट एटम विच हैव मैग्नेटिक मोमेंट जिनकी डायरेक्शन डिफरेंट होती है और वो एक दूसरे को कैंसिल आउट करते हैं. हाउएवर इन फेरी मैग्नेटिक सब्सटेंसेज although they have magnetic moments in opposite direction, but the magnitude of the magnetization is different. Their magnetic moments magnitude is different. So for example, for iron and magnetite की बात करें Fe3O4 की, so for example iron has higher magnetization as compared to the oxygen. So though they will be in opposite direction, so they will cancel out each other's effect, but they cannot completely cancel out each other effect because their magnetization or magnitude of magnetic is different. So in these materials the magnetic moment do not cancel out since they have the different magnitude, which result in a net spontaneous magnetic moment. This we can see in the following diagram. इसमें देखें कि ये हमारे पास जैसे ferromagnetic substances हैं, they are compound of two atoms. So here we can see we have in the first diagram we can see that the two atoms have magnetic moment in opposite direction, but the magnitude of magnetization is different. So that's why although they cancel out each other, but they cannot completely cancel out each other. So that's why there is still remains a magnetic moment. Similarly, we can see the second diagram, which is maybe give you better idea that we have magnetic moment shown for different atoms, which are two different atoms here, and we can see that their magnetic moments are in opposite direction. They are anti-parallels, however their magnitudes are different, so they partially cancel out each other's effect, but still a net magnetization remains. So such materials are known as ferromagnetic substances. So let's now summarize the three types of magnetism we studied today. So first one is ferromagnetism, then anti-ferromagnetism, and then ferromagnetism. जैसे हमने पहले डिस्कस भी किया कि द डिफरेंस बिटवीन दीज इज कि जो फेरोमैग्नेटिक है इसके अंदर जो मैग्नेटिक डोमेन्स एंड दे आर अलाइन इन पैरेलल टू ईच अदर एंड एज वेल एज द applied magnetic field. So here we can see in under the spin orientation within a domain के जो उनकी जो magnetic moments हैं they are aligned parallel to each other. जबकि in anti-ferromagnetism हम देख सकते हैं कि they magnetic moments and they are anti-parallel to each other और उनका जो magnitude है that is almost similar. So that's why they cancel out each other's effect and the result is the zero net magnetic moment. जबकि इन फेरीमैग्नेटिज्म जो हमारे पास है उसके अंदर हम देख सकते हैं कि हमारे पास जो मैग्नेटिक मोमेंट्स हैं दे आर एंटी पैरेलल टू ईच अदर, लेकिन जो उनका मैग्नीट्यूड है दैट इज़ डिफरेंट फ्रॉम वन अनदर. तो इस वजह से जो है वो कुछ जो मैग्नेटाइजेशन होती है उसको कैंसिल आउट हो जाती है, बट स्टिल जो है थोड़ी सी जो है उसके अंदर मैग्नेटाइजेशन जो है वो रहती है. और जो है इसके बाद डिफरेंट एग्जांपल्स हैं जो आप इनके सामने देख सकते हैं इन तीनों टाइप्स मटेरियल्स की. एंड अगर हम इसको समराइज़ करना चाहें कि हमारे पास जो एलिमेंट्स हैं इन पीरियोडिक टेबल, सो हेयर इज़ द पीरियोडिक टेबल जिसको अरेंज किया गया है. सो बेस्ड ऑन डिफरेंट कलर यू कैन सी के जो वाइट हैं जो कलर्ड नहीं हैं दे आर और पैरामैग्नेटिक, जो ग्रीन वाले हैं दे आर डायामैग्नेटिक एंड you can also see anti-ferromagnetic and ferromagnetic substances. और यहाँ पे we can see कि जो आपके आ रहे हैं कि जो बहुत थोड़े से ऐसे हैं कि जो ferromagnetic हैं या anti-ferromagnetic हैं, and but this टेबल जो है ये शो कर रहा है, दिस इज़ द शोइंग द प्रॉपर्टी ऑफ द बल्क मटेरियल, कि जो एज अ बल्क मटेरियल होता है. सो जो हम आगे स्लाइड्स में डिटेल में पढ़ेंगे कि फॉर एग्जांपल हम जिंक की बात करते हैं या कॉपर की बात करते हैं हेयर इन, तो ये जो है वो डायमैग्नेटिक हैं, लेकिन इनकी प्रॉपर्टीज़ को जो है वो चेंज किया जा सकता है क्योंकि हम वी आर दिस लेक्चर इज़ अबाउट एडवांस मटेरियल, सो वी कैन मॉडिफाई दिस एंड वी कैन मेक देम एंड फेरोमैग्नेटिक एक्चुअली, and we will inshallah now study that in detail. So we have learned different types of magnetic substances, and now we will move towards the magnetic properties of advanced materials. Or before we go into that, there are few terminologies जिसका आपको पता होना चाहिए. So most important जो magnetic substances हैं हमारे पास ferromagnetic substances हैं. So we will have 2 more slides about ferromagnetic substances, and we will also learn about hysteresis or soft or hard magnet क्या होते हैं, and what is remanent magnetization and coercivity, and we will learn these things, and then we will in next move towards the magnetic properties of advanced material. So जैसे कि हमने पढ़ा है पिछली स्लाइड्स में कि दैट फेरोमैग्नेटिज्म जो है ये मोस्टली आयरन, कोबाल्ट और निकल के अंदर होता है. सो अदर जो हैं वो मोस्टली जो डायमैग्नेटिक सब्सटेंसेस हैं उनको भी हम फेरोमैग्नेटिक बना सकते हैं थ्रू डिफरेंट मॉडिफिकेशंस. बट द फेरो जो है जो टर्म है बेसिकली इट वाज यूज्ड बिकॉज आयरन वाज टेकन एज द मैग्नेटिक मटेरियल. सो जो फेरो है ये वर्ड एक्चुअली यूज़ किया जाता है फ्रॉम फेरस, लेकिन जो है इट इज़ नॉट ओनली रिस्ट्रिक्टेड, द फेरोमैग्नेटिक सब्सटेंसेस आर नॉट रिस्ट्रिक्टेड टू द आयरन ओनली, बट ऑल अदर मटेरियल्स विच शो द such kind of behavior are known as ferromagnetic substances. अच्छा, इसमें यह है कि हमने पढ़ा है कि इट इज़ अ काइंड ऑफ वी कॉल इट अ कोऑपरेटिव फिनोमेना, क्योंकि जो इसके अंदर डिफरेंट पार्टिकल्स होते हैं, जो डिफरेंट डोमेन्स होती हैं, दे अलाइन देमसेल्फ according to each other, not only according to the applied magnetic field, but they cooperate with each other and they align themselves in parallel to each other. So that is the reason that their reaction is added up, their action is added up, और उनका जो magnetization होती है वो increase होती है, and that's why they are known as the permanent magnet. लेकिन one thing you should understand कि there are many ferromagnetic substances के they are ferromagnetic material, बट उनके अंदर जो है वो नॉर्मली मैग्नेटाइजेशन नहीं होती, दे आर नॉट मैग्नेटिक, क्योंकि उनके अंदर जो वाइस डोमेन्स होते हैं वो एक दूसरे का अफेक्ट को कैंसिल कर रहे होते हैं, क्योंकि उनकी जो डायरेक्शन होती है, जो डोमेन्स होते हैं वो कम्प्लीटली अलाइन नहीं होते पैरेलल टू ईच अदर. सो दैट्स वाई वो एक दूसरे का जो अफेक्ट होता है उसको कैंसिल कर रहे होते हैं. सो टू मेक अ फेरोमैग्नेटिक सब्सटेंस मैग्नेटिक, उनको पहले जो है वो एक एक्सटर्नल मैग्नेटिक फील्ड अप्लाई करना पड़ता है. When we apply that external magnetic field, their magnetic domains और vice domains वो parallel एक दूसरे को अरेंज कर लेते हैं, और उसके बाद अगर हम magnetic field रिमूव भी कर दें तो वो magnetic रहते हैं. बट एटलीस्ट वन टाइम जो है उनको जो है वो external magnetic field जो है उसके अंदर रखना पड़ता है to make them permanent magnet. So in ferromagnetic substances जब हम external magnetic field remove करते हैं, still it retains magnetization, and that phenomena is also called as hysteresis. And when we draw a plot between variation of magnetism with applied magnetic field, it is known as hysteresis loop. So let's see in this coming diagram कि यहाँ पे हमारे पास जो है वो एक्स एक्सिस पे जो है वो हमारे पास एच है जो कि है अप्लाइड मैग्नेटिक फील्ड या एक्सटर्नल मैग्नेटिक फील्ड, और हम इसके अंदर वेरिएशन देखते हैं कि जैसे हम अप्लाइड जो मैग्नेटिक फील्ड है, एक्सटर्नल मैग्नेटिक फील्ड है, उसकी जब स्ट्रेंथ को इंक्रीज़ करते हैं तो उसकी जो फेरोमैग्नेटिक सब्सटेंस है उसकी मैग्नेटाइजेशन पे क्या असर पड़ता है. सो ये जो प्लॉट है इसको हम जो है वो हिस्टेरेसिस लूप कहते हैं. सो एज वी कैन सी इन दिस डायग्राम के जब हम ज़ीरो पे जाते हैं, एक्स और वाई पे जो सेंटर है वहाँ पे, तो जब यहाँ से हम अप्लाइड मैग्नेटिक फील्ड इंक्रीज़ करते हैं तो हम क्या देखते हैं कि जो इसकी मैग्नेटाइजेशन है वो भी इंक्रीज़ होना शुरू हो जाती है. और इंक्रीज होते होते जो है वो एंड पे जाके ये एक हमारे पास लाइन जो है वो स्ट्रेट हो जाती, विच मीन्स कि जो मैग्नेटिक सब्सटेंस है ये सैचुरेट हो गया, दैट मीन्स इट हैज़ गेट द maximum possible magnetization. So after that when we remove the magnetic fields, so we can see कि जब हम इसको मैग्नेटिक फील्ड को ऑफ करते हैं तो आप ज़ीरो पे आ जाएं तो हम देखते हैं कि जो हमारे पास जो लूप है, जो मैग्नेटाइजेशन है, वो ज़ीरो नहीं है बल्कि वो काफ़ी ऊपर है. यहाँ पे हम आपको ये रेड नज़र आ रहा है, स्मॉल जो बॉल्स है जिसके साथ रिटेंटिविटी लिखा है. तो इट मीन्स कि इसनी जो है मैग्नेटाइजेशन उसके अंदर रह गई है, इवन दो वी हैव रिमूव्ड और टर्न ऑफ द एक्सटर्नल मैग्नेटिक फील्ड. सो दिस इज कॉल्ड रिटेनिटिविटी भी कहते हैं और इसको रेमनेंट मैग्नेटाइजेशन भी कहते हैं, कि जब आप एक्सटर्नल मैग्नेटिक फील्ड अप्लाई करते हैं वो और सेचुरेशन तक लेके जाते हैं, और जब आप मैग्नेटिक फील्ड ऑफ करते हैं तो ज़ीरो मैग्नेटिक फील्ड पे उसके अंदर जितनी मैग्नेटाइजेशन रह जाती है उसको रेमनेंट मैग्नेटाइजेशन कहा जाता है. अब इसको ख़त्म करने के जो है वो जो रेमनेंट मैग्नेटाइजेशन है, इसको अगर हमें ज़ीरो करना है तो उसके दो प्रोसेस होते हैं. फर्स्ट मेथड इज़ दैट क्या वी इंक्रीज द टेम्परेचर, हम टेम्परेचर इंक्रीज़ करेंगे तो उससे क्या होता है कि जो हमारा मटीरियल होता है बिहेव जस्ट लाइक पैरामैग्नेटिक में हमने देखा था कि जैसे ही हम टेम्परेचर इंक्रीज़ करते हैं तो वो डीमैग्नेटाइज हो जाता है. एंड सेकेंड ऑप्शन इन सच ए केस ये है कि हम नेगेटिव मैग्नेटिक फील्ड अप्लाई करें यहाँ पे, तो उससे ये होगा कि जो है ये मैग्नेटिक मटेरियल जो है वो डीमैग्नेटाइज हो जाएगा. एंड जैसे कि आप इसमें देख सकते हैं कि जब हम डायग्राम के अंदर जहाँ पे कोर्सिविटी लिखा हुआ है कि ये जो ब्लू डॉट है कि जब हम अप्लाइड मैग्नेट माइनस एच करते हैं, दिस इज़ द कि मतलब ये है कि हम अपोजिट डायरेक्शन में अप्लाइड जो है एक्सटर्नल मैग्नेटिक फील्ड अप्लाई कर रहे हैं, तो व्हाट हैपन्स कि जो इसके अंदर मैग्नेटाइजेशन रह गई थी वो ख़त्म हो जाती है और वो ज़ीरो मैग्नेटाइजेशन आ जाती है. ये जो स्ट्रेंथ ऑफ मैग्नेटिक फील्ड है कि जो हमें अपोजिट डायरेक्शन में अप्लाई करना पड़ रहा है, दैट एक्चुअली इज़ कॉल्ड कोर्सिविटी. कोर्सिविटी क्या है कि इट इज़ द फोर्स और मैग्नेटिक फील्ड रिक्वायर to demagnetize the ferromagnetic substance. So these are the very important terminologies जो कि हमें आगे जाके आपको देखेंगे इनको, डिपेंडिंग ऑन द कोर्सिविटी क्या है और उसके अंदर रेमनेंट मैग्नेटाइजेशन क्या है. These are really important for the application point of view of ferromagnetic substances. So now let's start with the magnetic properties of advanced materials. And मोस्टली जो हमारे पास इनऑर्गेनिक सॉलिड्स हैं दे affect I mean they exhibit different magnetic properties other than diamagnetism, so they are important for their use in different applications. And we know that to be for a material to be a magnetic, they should have unpaired electrons in their valence shell. So normally the transition metal elements or lanthanides they have unpaired electrons in their D and F shells respectively, so they are mostly used for the application where magnetic properties are required. We already discussed कि जो unpaired electrons होते हैं they induce the magnetization in materials through different way, either they are through spin or their orbital motion, so they are really important for a material to be magnetic in nature. और some of the magnetic oxides, one of the common application है magnetic materials that is used in the transformers जो आपके use होते हैं बिजली के. So their core is actually made of magnetic material which is MgFe2O4, and there are some other magnetic oxide as well which are used for that purpose nowadays. And also there these magnetic oxide, other than the transformer cores, they are also used in the रिकॉर्डिंग एंड इंफॉर्मेशन स्टोरेज डिवाइसेस. जैसे हमारे पास हार्ड डिस्क वगैरह होती हैं कंप्यूटर की, तो उसके अंदर भी जो है इनको यूज़ किया जाता है मैग्नेटिक ऑक्साइड्स को. So depending on the application where we are using those magnetic materials, so we require different strength of magnetization or different hardness of magnetization. So what is hardness in case of magnetic material? What are soft magnets and hard magnets? So let's look at this diagram, which is the hysteresis plot. So यहाँ पे we can see hysteresis, two hysteresis actually, one is written soft and one is the written hard. So here we have used different numbers, which is S is equal to saturation magnetization, कि maximum कितना है उसके अंदर में जो है magnetization हो जाती है. R is the remnant magnetization, that how much magnetization remains when we remove the external magnetic field, and K is the coercive force. So negative K is the amount of negative magnetic field which is required to demagnetize a material. So those materials which require very low negative field or external magnetic field to make them demagnetized are known as soft magnetic materials. In hard magnetic materials, we need a large coercive force which is minus K. So we need a large force or large magnetic field to demagnetize a material. So these materials, thus we categorize these materials as soft and hard. And depending on the application, there are different applications which require soft magnetic material, और कई ऐसी application है where we need hard magnetic material. So depending on the application, we choose the material we have to use. For example, जो हमारे हम direct जो current, जो DC current electric motor use करते हैं, so that should have a high coercive force to maintain its magnetization. So there we will use the hard magnetic materials. And similarly, there are other applications where we need soft material, which we will discuss in the next slide. And soft magnetic materials which have the small coercive forces, they are required in other application. For example, in the recording heads they are used. So any application जहाँ पे जो है उसकी आपके पास fast and frequent जो है आपको उसकी remagnetization या demagnetization require हो, so there we use the soft materials. For example, जो हमारे पास जितने भी इलेक्ट्रिकल एनर्जी के लिए जनरेशन के लिए है, आइदर इट्स फॉर कन्वर्जन है, जो ट्रांसमिशन के लिए जो मैग्नेटिक मटीरियल यूज़ होते हैं, दे आर मोस्टली द सॉफ्ट मैग्नेटिक मटीरियल्स. However, there are many applications where hard magnetic materials are required, and because of for example in जो हमारे electrical vehicles होती हैं, so they required actually hard magnetic materials. Their soft magnetic materials are not efficient in the electric vehicles. So they are really important. The permanent magnets or the hard permanent magnet are very important in electrochemical applications. So there is a very important application of these magnetic materials is the magnetic refrigeration, and that actually depends on, we call a terminology which is magnetocaloric effect. So what is that magnetic refrigeration? So I'm not actually going to answer that terminology, and it's for you guys to look after, and it's your, you whether take it as homework or assignment. So you have to, after this lecture, you have to Google these terminologies and try to understand these terms. What are these and what is the magnetocaloric effect? Another very important application of magnetic materials in biomedical research and one of the most hot topic is the use of nano carriers which are based on magnetic materials for the anti-cancer therapy. So there are many other applications in which magnetic materials are nowadays used in the biomedical research and this is a very rapidly growing area of the research nowadays. However, when we talk about the use of magnetic materials for different applications, so the understanding the correlation between a magnetic property of a material and its structure or nanostructure is really important for potential applications. Depending आपने कहाँ पे किसी magnetic material को use करना है, so on the basis you have to synthesize those materials with a specific nanostructure, and that will actually enhance the efficiency of those substances for a particular application. For example, When we talk about platinum or gold, so we know that they are diamagnetic substances, so they are non-magnetic. But there are certain applications in which if we use platinum and gold, so they can be really beneficial if they can have magnetic properties, but we know that they are diamagnetic, so we try to make them magnetic. And there are different techniques which are used for making them magnetic, but one common technique is to reduce their size into the nano level. So if we make the nanoparticles or nanocrystals or whatever nanowires, so there can be multiple structures which are possible, so they can have the magnetic properties. So this is really important, the relation between the magnetic properties and the nanostructure of the material, and that will totally depend where we gonna use those materials. So we will synthesize them in that way, or we will make that structure of the material. And one of the important thing that we should remember, that non-ferromagnetic substances including zinc and platinum and some other materials, so they are non-ferromagnetic, they are diamagnetic, so they may exhibit even ferromagnetic like behavior when they are in the nano range. So this is a really important point, that we can change or we can manipulate the properties of magnetic for non-magnetic materials and make them magnetic only through reduction of their size. And another common way of inducing magnetic properties in non-magnetic material is the surface modification. Okay, one possibility is that we reduce the size of the material so that they show ferromagnetic behavior. Another possibility is that we cap those surface or nanoparticles or the materials with some specific chemical compound or chemical species which make them magnetic. And this process of capping the materials with appropriate molecules is really important, that it can manipulate the characteristic of materials and especially the magnetic properties of that materials. So we can get the ferromagnetic properties from those materials which are actually diamagnetic in nature through surface modification using different chemical compounds. Advanced materials with tuned electrical and magnetic properties are the goal of all material scientists. So there are different applications where magnetic materials are used, their electrical materials are used. In some cases, for example, if we have a material which is a semiconductor material and however it is not magnetic, so there are many applications. For example, in spintronics, के जहाँ पे ऐसा मटेरियल विच शोज बोथ सेमी कंडक्टिंग एंड मैग्नेटिक बिहेवियर, दे आर रियली इम्पोर्टेंट. एंड फॉर दैट पर्पस जो है उसको जो हमारे पास मटेरियल होते हैं, वी ट्यून देम, वी मैनिपुलेट देम थ्रू सम केमिकल मॉडिफिकेशन, सम साइज रिडक्शन, and we get the desired properties of from those materials for those specific application. So by manipulating the magnetic properties of different advanced materials or different materials, we can enhance the efficiency of different devices. For example, electronic devices, we can enhance the performance and efficiency of the hybrid जो हमारे पास electric cars आ रही हैं, उनकी efficiency we can enhance that. And also we are having some data storage devices, so we can also enhance their efficiency and we can use them in a better way and more efficient way. So the magnetic materials are really important for all of these applications. So a good control of their magnetic properties through their size reduction or capping actually determines how efficiently we can use those magnetic materials for that certain application. Let's take another example. So the strongest जो permanent magnet which is currently used is the composite material of neodymium, iron and boron, which was made in around 1984, and after that it has being used in many applications. For example, in the magnetic storage devices, या जो हमारे पास electric जो vehicles होती हैं, their motor is actually they contains that neodymium iron boron composite magnets, because for currently these are the most strongest permanent magnets available. So these are also used for magnetic resonance imaging. Beside the hard disks, they're used in the magnetic storage devices, and they are also used for sensors and high performance motors for hybrid electric cars. But a problem is that although they are they are very strong permanent magnet, but still at high temperature, because when we are dealing with the cars or vehicle engines, so their temperature is very high over there, so their efficiency is actually still suffers at high speeds and high temperature. So that still that is a current problem which the scientists are having while working on the electrical vehicles. So how can we solve that issue? Okay, how we can कैसे हम इसको रोक सकते हैं कि जो इसकी कोर्सिविटी है वो रिड्यूस ना हो एट हाई टेम्परेचर? हाउ कैन वी मॉडिफाई दैम? सो what is the solution for that? So one of the first step which we have to take to improve their properties is to know them or know their characteristics at the very nano level. So for that, these days some very efficient electron microscopes which have the resolution of atomic level, they are being built, which are available and help the scientists to study these materials at the atomic level, especially these kind of composite materials for their high functional applications. And the use of these very hi-fi techniques is actually helping the scientists and the material researchers to understand how they can improve their properties and how they can manipulate their properties for a specific application. We will take an example. For example, we have lanthanum ferrite and the strontium titanate. So this composite material actually have both of them, both lanthanum ferrite and the strontium titanate have different properties, but the interface where they both join, if we look at the subatomic level, so there are some specific interaction on the interface of both these, which result in specific properties which are not found in both of these materials. However, at their interface they exhibit very special properties which can be used for specific application. Similarly, for our question that how we can improve the neodymium iron and boron composite, how can we avoid the reduction in their coercivity at high temperature? So electron holography actually that is used by the researchers to study magnetism of those very thin, in the range of around nanometer जो है grain boundary जो है neodymium iron and boron की. So at very nano level they have studied and they have tried to tweak or manipulate those interfaces, interaction between these, and they have improved the certain magnetic properties, or the reduction in the coercivity has been reduced by their modification. However, still there is a work going on that material, because अभी तक जो है वो इतना अच्छे जो है वो मैग्नेट अभी तक उन्होंने नहीं डेवलप किए कि जो बहुत हाई टेम्परेचर पे भी अपनी जो है वो उसकी मैग्नेटाइजेशन को मेंटेन रख सकें. बट स्टिल द वर्क इज़ गोइंग ऑन, एंड बट दैट्स द सोल्यूशन कि आप बहुत नैनो लेवल पे, एटॉमिक लेवल पे जाके आप देखें कि वो जो परमानेंट मैग्नेट है, वाई दैट इज़ द स्ट्रॉन्गेस्ट मैग्नेट, एंड जब इसकी अगर कोर्सिविटी रिड्यूस हो रही है हाई टेम्परेचर पे, तो हम उसको कैसे जो है उसके अंदर जो है वो उसको इम्प्रूव कर सकते हैं. एंड दैट इज़ ओनली पॉसिबल इफ़ वी गो टू द सब एटॉमिक लेवल. So that was different applications of the magnetic materials, especially for advanced magnetic materials which are used for certain advanced or high-fi application for electric vehicles and those things. Overall, if we see, there are many materials, there is a vast variety of advanced materials which are used for certain magnetic applications, whether it is for data collection or processing, or for data transmission, storage, or display information, or electrical vehicles. So there is a huge variety of magnetic materials or advanced magnetic materials which are used nowadays in the different industries. एंड आप इसकी जो एडवांस मटेरियल्स फॉर मैग्नेटिक एप्लीकेशन, इसकी इंपॉर्टेंस का अंदाज़ा इससे लगा सकते हैं कि नाउ पीपल फ्रॉम डिफरेंट फील्ड, जैसे फिज़िक्स है, केमिस्ट्री है, इंजीनियरिंग है एंड द मटेरियल साइंस, सो द पीपल फ्रॉम ऑल दिस फील्ड्स आर वर्किंग टुगेदर एंड दे आर कन्वर्जिंग to make these materials better and more efficient for certain high-end application. For example, the hybrid electrical vehicles or normal electrical motors which are used, and also for spintronics application. And there are so many advanced fields where these advanced magnetic materials are used, and the work is going on by different engineers, chemists and physicists to enhance further the magnetic properties of these materials. And also there is work going on to synthesize new materials which can show the better magnetic properties. So thank you so much for listening and for your patience during the lectures. I really hope that you have understood at least a few concepts from this lecture. But in case you have any question or you don't understand anything from the lecture, so you are really free to ask me those questions and I will be happy to answer those. Thank you so much and Allah Hafiz.